Welcome to this video. Today I will be talking about state discrimination task. This is a video after many days, and I will try to also upload videos more regularly. State discrimination, as I have written in the heading, it's an important task in quantum information theory, and in the next video we will see that how it relates to the task of subchannel discrimination, which provides some useful characterization of convex sets inside the set of density matrices. So first let's frame the proper stage of the state discrimination task. So we have a state rho, and this state, the question is, this state is chosen from an ensemble P0 which has rho 0 and P1 which has rho 1. So it's like a bag, and from the bag we can choose with probability P0 the state rho 0, and with probability P1 the state rho 1, and then we can perform measurement on this state. So I have my measurement apparatus. It's a POVM set of measurement. So there are two measurement elements, M0 and M1, and then we will record the output. So then we record the output, and the idea is sometimes there is a click of 0, sometimes there is a click of 1, and when 0 is the output, we say state was rho 0, and when 1 is in the output, the state was rho 1. So this is the basic setup, and what one must remember that the initial ensemble, it has rho 0 with probability P0 and rho 1 with probability P1. So this is like a classical probability. You can think about some third person tossing a biased coin, and based on biased coin giving you the state rho 0 or the state rho 1. So here I can say that, for example, there is some third person who has a coin which is biased, and its probability P0 is head, and with P1 the probability is tail, and based on this he prepares the state rho 0 or the state rho 1. So this is the main setup, and now the idea is we have to calculate the success probability that we correctly get the prediction. So this is given by P0 rho 0 with M0 plus P1 rho 1 with M1. So this inner product is just the trace inner product or Hilbert-Schmidt inner product. So this is nothing but trace rho 0 M0, and similarly this is trace rho 1 M1. And the idea is with probability P0, I correctly guess my state. What is the probability of that? It is the detector measures M0. So this is the probability of measuring M0 when my state is rho 0. So this is basically the success probability. So what is the probability that my detector clicks at M0? So I register output 0 when the actual state is 0. So one can also say probability of failure, which is nothing but P0, and here rho 0 and M1 appears because I wrongly say that my detector clicks at 1 when my state was actually 0. So these are the two probabilities, probability of success and probability of failure. And now what is the main theorem? The main theorem is the Holevo-Helstrom theorem that we are going to discuss in this video. It says that, so let me just write the theorem name, Holevo-Helstrom theorem. So this theorem says or rather gives a bound on this probability of success and probability of failure. It's easy to see that the lower bound on probability of success is actually the upper bound on probability of failure, and vice versa. So with this we can write that probability of success. So what is the main gist of the theorem? It is probability of success has an upper bound of 1 plus not P0 row 0 minus P1 row 1, and the lower bound is given by, so this is the upper bound of probability of failure, 1 minus P0 row 0 minus P1 row 1, like this. So this is the main theorem, which is called Holevo-Helstrom theorem. So I can at most fail by this amount, and I can at most succeed by this amount. So for example, first one, for example, I have row 0 is the state 0 0. So row 0 is 0 0, and row 1 is 1 1, and P0 equal to P1 equal to half. This means that I have an ensemble which is with probability half 0 and with probability half it's 1. And the idea is you can achieve a success probability of 1. So P success can be equal to 1 with the projectors with M0 equal to 0 0 and M1 equal to 1 1. So you can check that if I put this if I put this particular thing here in this particular equation, then what I have is half times you have this row 0, which is 0 0 M0, the overlap is 1, and here also overlap is 1, so PS is equal to 1. So the second example, which is a bit more complicated, it is row 0 is 0 0 and row 1 is plus plus. So there is a non-zero overlap between the states, and P0 P1 is again half. So in this case it can be shown that by this PS, so PS has the upper bound of 0.85, so it is half 1 plus 1 over root 2. So this upper bound is obtained for M0 equal to a particular state VV, and M1 equal to identity minus VV, because these are anyway POVMs. So M0 plus M1 is identity. And what is this state V? The state V is of this form. It is some normalization alpha times 1 minus 1 plus square root 2 0. So the question is, how did I get this state? So this is the question, and this question will be addressed when we look at the proof of the Holevo-Helstrom theorem. So I hope the theorem is clear, and we can write the theorem in a better fashion if we perform some simplifications. So simplification. So the simplification is suppose P0 and P1 both are half. So it is always that I have I'm flipping a unbiased coin. So here this coin was biased, but I am flipping now an unbiased coin. And if this happens, then we can say that the particular expression simplifies to the trace distance. So the norm, the one norm, so we have norm of x is equal to trace under root x dagger. So this is the norm, and this norm, so half of norm row 0 minus row 1 is the trace distance between row 0 and row 1. And this can be seen that what we get here is exactly the trace distance in the upper bound and the lower bound. And further, the trace distance can be simplified to fidelity if we have states which are pure states. For example, in this example I had the pure state, so let me use a different color. So here you can see these states are pure states, and in this case what I have is P success is always less than equal to Let me see. It will always be less than or equal to half 1 plus under root 1 minus mod AB square. So this is the fidelity. This is fidelity, and this is basically the expression of the PS, which is exactly the expression that we have here. Okay, now let's try to discuss the proof of this particular theorem. So the proof, I will divide it into three parts. The first two parts will be simplification of the basic basic statement of the theorem, and the third part will be the actual proof. So for this, we say that rho 0 tilde, let it be p0 rho 0. This is one thing, and let rho 1 tilde be p1 rho 1, and then rho 0 tilde minus rho 1 tilde, this is equal to h, which is equal to summation over I lambda I. So here what I have done is simply taken the difference, and I am calling the difference a Hermitian matrix, which can be diagonalized in some particular basis, and this basis can be chosen to be orthonormal, and this can be written as q minus s. So here what I am doing is, from these lambdas, I am actually collecting the positive eigenvalues and saying that they form q, and the negative eigenvalues I am saying that they form s. So this is the main idea. So here both q and s, so q and s both are greater than or equal to 0, both are positive semi-definite, because I have already taken out the minus sign here, and more importantly, q dot s is 0. This is because they are I have separated the positive eigenvalues and negative eigenvalues, and they are orthonormal. I can choose the vectors, the eigenvectors, to be orthonormal. So this is just the orthogonality condition. Now what we are going to do is we are going to use this later on. So now let's look into the second part. So this was the first part. So now the second part. So the second part is to consider m0. Take m0 is equal to 1 minus t by 2. This is just a redefinition, like I am redefining m0 and m1 to be 1 plus t by 2. And here I know that m0 satisfies this constraint, m1 also similarly. So this means that t satisfies this particular constraint. So this you can check easily by putting m0 as this expression here. So this is nothing, just redefinition of variables, and with this ps is given by ps was rho 0 tilde m0 plus rho 1 tilde m1, and this is equal to I will write it in terms of t. So this is equal to half, I'm taking the half out, so I have 1 plus trace t times rho 1 tilde minus rho 0 tilde. This again it can easily be checked, which is equal to, so this is equal to half bracket 1 minus trace t times rho 0 tilde minus rho 1 tilde. So here the bracket closes. So I have now two expressions. So let's use a different color. So I have these two expressions, and you can easily see that these expressions are exactly of the form of the formula of Holevo-Helstrom theorem, the upper bound that we have. So if you see in the theorem, it is exactly having a half outside, and inside I have 1 plus something, but here that something is not quite there yet. So for this, what we need to prove, so what we need what we need to prove is max over minus 1 t plus 1, or identity, because t is an operator here. It just means the same thing. So a trace of t times rho 1 tilde minus rho 0 tilde, this is equal to, and this we have to prove, this is equal to the definition, the kind of a similar statement or similar expression of the norm that we have, the rho 0 tilde minus rho 1 tilde. So this is kind of the trace distance. This is the trace distance, and trace distance can be written in terms of an optimization problem. This is what we have to prove. So in other words, this maximization here would correspond to maximizing this term, and we will get maximum value of PS. And if I maximize t trace t times the opposite thing, this should also be equal to the trace distance, because the trace distance itself is symmetric. It better be equal. So this means that in the second expression that I have, in the second expression I can talk about maximizing this term so that I minimize my PS. So one expression is talking about maximization and one expression is talking about minimization. Now let's see how we can prove these two expressions easily. So here I have these expressions and I'm going to prove them. So let's prove them. So this is the step 3, part 3. So here rho 0 tilde minus rho 1 tilde is equal to trace of Q plus trace of S. So remember that rho 0 minus rho 1. So let's come above. So here rho 0 minus rho 1 was Q minus S. But now what I am doing is I am taking the norm basically. So here when I take this norm, what I will do is I will do rho 0 tilde minus rho 1 tilde. I will square it and then take the under root and take the trace, because this is Hermitian, its conjugate is itself. So this expression that I have in here, this will evaluate to Q plus S, because why I am getting Q plus instead of minus, it is simply because I have lambda I some lambda n as positive values whose mod is positive. So this is in Q, and then I have minus omega 1 to omega k, which are in S basically, but because I am taking the mod I will get a plus sign. So that's the point. So this is Q plus S, and then I am taking the trace here. So this gives me this particular expression. And now what we can do is basically, let's see. So now the next step will be to take the expression that we have here, trace Q plus trace S, and simplify it. So trace Q plus trace S, we will write it in a better form. So for this, notice that trace of rho 0 tilde minus rho 1 tilde, this is equal to P0 minus P1. This is simple, and this is also equal to trace of Q minus trace of S. So this is simple, because this we have defined rho 0 minus rho 1 as Q minus S. So trace Q plus trace S can be written as 2 times trace of Q plus P1 minus P0. That is using this expression. Now this can be written as, now here comes an important point, that this can be written as 2 times trace of projection onto Q of rho 0 tilde minus rho 1 tilde minus trace of rho 0 tilde minus rho 1 tilde. So this we can write. So let's look into this, why we can write this. So here rho 0 minus rho 1, so let me use a different color. Rho 0 minus rho 1 can be written as q minus s, right? And when I project onto the q sector, because q and s are orthogonal sectors, I will only get this contribution. So so this entire thing that I have here, it is just simply trace of q. I think this makes sense. So here I have trace of q. This is just the same term, and the next term is just p1 minus p0 along with the minus sign if you take it inside. So now what this means is that we have a new formulation of rho 0, the norm. So norm of rho 0 tilde minus rho 1 tilde is equal to trace of 2 times projector onto q minus 1 rho 0 tilde minus rho 1 tilde. So this comes from the previous calculation, and now I can put a minus sign also to get trace of 1 minus 2 pq rho 1 tilde minus rho 0 tilde, and we are almost done, because notice that these operators that I have here, these two, they both are like the t operators. They are between minus 1 and 1. And why is this? This is because the projector is always positive semi-definite. So p is always greater than, so pq is always between 0 and 1, because p square is equal to p and the eigenvalues are 0 or 1. So this holds, and this in turn means that 2 times projector minus 1 is between minus 1 and 1. So this means we have shown that there is a t. So let's write. So there exists a t such that I call this t star, for example, such that norm rho 0 tilde minus rho 1 tilde is equal to trace of t star, for example 1 times. So here I have two different t stars, right? Where is this? So here I have two different expressions which are exactly same, so I should remember that. So one is 2p minus 1, that is rho 0 tilde minus rho 1 tilde, and which is equal to trace of t 2 star rho 0 no, this is not correct. It is rho 1 tilde minus rho 0 tilde. Now I have to show that any other t that satisfies this condition is always lower bounding it. So this is really the max that you can get. So for this it is quite simple to show this. So what we need to do is simply observe that trace of t rho 0 tilde minus rho 1 tilde is trace of tq minus trace ts, which is less than equal to trace of q plus s, which is equal to exactly rho 0 tilde minus rho 1 tilde. So similarly it can be easily shown that trace t times rho 1 tilde minus rho 0 tilde is also less than equal to norm rho 0 tilde minus rho 1 tilde. So why this holds? Let's quickly see. So t is between minus 1 and 1, and q and s are positive semi-definite matrices, so I can multiply them. So tq keeps the sign of inequality, so I have something like this, and similarly I can multiply with minus s to get something like this. So So with this, what we have shown is max of -1 t1 trace of t times rho 0 tilde minus rho 1 tilde is equal to the norm, kind of the trace distance between rho 0 tilde and rho 1 tilde. So this is what we have shown, and this in turn means that we have shown the Holevo theorem, basically, because in the Holevo theorem, if you observe, from here rho s that we have, it had this exact expression, and this expression is equal to the norm, basically, that we have shown. So ps is less than equal to that it is half bracket 1 plus norm rho 0 tilde minus rho 1 tilde, and on the other side it is half 1 minus norm rho 0 tilde minus rho 1 tilde. Now, which projectors get or saturate this? So saturation. So this is also simple to see. The projector is basically t equal to 1 minus 2 pq. So if t is 1 minus 2 pq, then m0 is equal to, so what is m0 here? So m0 is this expression, 1 minus t by 2, that is equal to pq. So this means that if I take my POVM to be projector along the positive eigenvalue, so basically I take rho 0 minus rho 1, and then I calculate q minus s, and then I use the projector onto q. So basically I perform a spectral decomposition of q and then collect all the eigenvectors. So this is summation over I lambda qi. So this is actually the POVM element that saturates it. So this, and m1 is automatically 1 minus pq. So with this, I have discussed this entire idea of proving the Holevo-Helstrom theorem. It is a bit of lengthy. The proof is lengthy, but the theorem is very clear. And in the next video, I will be talking about how this theorem is useful in sub-channel discrimination, which follows a paper by some authors, particularly Ryuji Takagi and other authors. So let's see. With this, I end my video.